Hey classes, welcome back. Try and give a quick recap of where we've been this week, where we're going in week 26. Can't believe it's week 26 already. Getting ready for another atmospheric river to hit this week. Let's jump on into some of the things that we've been talking about in class and some of the things that we've had to turn in already in the beginning of the third trimester. We've been doing the anatomy of the eye, and if you check out this picture right here, this should be in the students' notebooks right now. If you want to check the students' notebooks, make sure this is in there because we're not just learning the parts and going through the parts of the eye, which is important. We do that in 6th grade, but also, let me put that down, going through a little bit on how the eye connects with the brain. If you look at this picture right here, one of the standards talks about myopia and farsightedness, nearsightedness, how we correct for those. That's where we get into the lenses. Now, the lens can focus light, of course, onto the retina, but one of the little experiments we did to show how the light, when it hits the retina in the back of the eye, let's say you have normal vision, like me right now with my reading glasses on, you can try this at home. Take a piece of paper and you put a dot on the left side and an X on the right side. If you look at something like this, and you close your right eye and you bring it in just to the right spot, you can find your own personal blind spot. We all have one. This ties into not only the anatomy of the eye, the fact that there's no rods and cones right there where the optic nerve takes the information up to the brain, or right straight to the brain, I should say. There's no rods and cones there, so there's no information for that one spot in your vision. Now, if you have normal binocular vision, the other eye will, of course, see that blank spot. But here's the thing, as you close one eye and you do that test, there is technically a blank spot that should be there, and yet we don't see it. We don't see like a big black patch right there where there's just no vision. Instead, our brain, this gets into brain anatomy, what we did a little bit with the Dr. David Eagleman clip that we saw with brain science. You actually have your brain filling in, based on experience, what should be there. In other words, part of our vision, part of what we do with our visual connections with our brain fills in based on our past experience what we think should be in that space. And so if you do this with the dot and the X, that's one example, closing your right eye again, bring it back and forth. You can try it also looking around a classroom like this. Now right now my classroom's empty, but as I close one eye, if you get it just right, if there's a student sitting there, if you cover one student at just your right spot on the blind spot, you'll just see a desk. In other words, your brain literally fills that in for you. I'll link down below the excellent Dr. David Eagleman special on that. Going a little bit deeper into lenses, we talk about how you correct using convex or concave lenses for farsightedness or nearsightedness. Also, a little bit about processing. Part of the Eagleman special focused on reaction time. And we first did a reaction time lab just the other day, where we were dropping, this is to get us used to the data gathering in this type of lab, dropping a meter stick, seeing how far it falls before we catch it when somebody else drops it, of course. What we did today then is take it another step because we really want to work on displaying this data to look for correlations, to look for positive, negative, or no correlations in the data. So what we did in class today was an online test. And you can check it out for yourself. I'll also link this one below. It's from the University of Washington, where the light turns green. You click on it as fast as you can, and you can test your own reaction time. You do it a couple times. It gives you an average. And when it gives you the average, we can then put it, just like you're doing in your math classes across the hall, we can then put it into an X and Y coordinate system. And again, we're looking for the correlations between the two. On the board over here, let me get on this side. A friend of mine took this picture this morning, and you might recognize that street cruising on down Fassler right there. As she cruised down Fassler, she was in the passenger seat, snapped a picture. You see the beautiful rainbow. Notice how it always goes from red down to blue. And when we're talking about the frequency of light, or the wavelength, I should say, of light, what you're experiencing as different colors is really just the different wavelengths of light. I'm going to turn off this board here and show you the brain pop that we had up on the board this morning. But remember, we started the year with something kind of like this. We had a rope with a weight hanging from it, and we were checking the frequency, and given a small amplitude, let it swing back and forth. We hopefully remember at this point in the year that it doesn't matter if we have one 500-gram weight at the end, or if we add it another one to it and get 1,000 grams at the end, it'll swing at the same rate. What really matters for your frequency is the length of the string. Shorter goes faster, longer goes slower. Related that to the length of baseball bats, golf clubs, try to tie it to a little bit of our sports science. And when we are looking at waves, let me grab this right here. Tomorrow, one of the stations that we'll have set up for the labs around the room tomorrow will include this right here. This is Ames tube right here. And if you check out frequency, wavelength, I will spare the students this time by not playing guitar for them, like I did last time, to talk a little bit about harmonic frequencies. But when we're talking about the wavelengths of sound, and the wavelengths in light can both be related with the same equation. As a matter of fact, it's stunningly amazing, all the places that the wave equation turns up. I even wrote it on my surfboard a little while ago, just because I'm that much of a geek when I'm out there in the waves. I get to look at the wave equation while I'm out there. And when you're looking at the velocity, frequency, and wavelength, I'd like you to keep in mind, this is a review note from several weeks ago, that in terms of light moving through the vacuum of space, light has a constant speed. The stunning implications of that is that since velocity is constant for light, then you must be changing speed or distance. You must be changing distance or length to make up for that. So we'll get into just a tiny, tiny bit of some of the implications of the speed of light being constant. When you look at the wave equation over here, it relates to what we're going to be checking out in class in person tomorrow, which is a little bit more, squeaky door today, a little bit more on the difference between reflection and refraction. If you look at reflection and refraction, we're not doing diffraction yet anyway. We will when we get a little bit more into the structure of the ear. We do sound, we do earthquakes. We'll talk about diffraction then. But we're talking about refraction, where light changes speed going through certain substances. If you have, for example, water versus glass, say a glass of water is going through versus a solid block of glass that's mostly transparent and the light can pass through, it will change its angle differently depending on the substance. This is called the index of refraction. In other words, if you are looking at the amount by which the ray appears to change, it will change differently depending on the substance it goes through. This can help us sometimes identify certain substances as well. And then over here, reflection. This is why we have under the table here, which I will try and pick up because it's kind of large, a small pool table. Yes, a pool table. We're checking out the way the billiard balls bounce off the wall and then come out again. So I'll be teaching your students how to be pool sharks, of course, in this class tomorrow. When you're looking at all of these things, I know I've talked kind of fast about a lot of things, but really what it comes down to is the way that waves reflect, refract, and the way that we take advantage of this in things like eyeglasses right here to correct for, in my case, farsightedness, and also the way that we apply these from everything from ocean waves to earthquake waves to learning about music to talking about the reflections that happen, for example, in tomorrow's lab when we bounce lasers. We have small laser pointers that we're going to bounce off of mirrors and try and determine for ourselves the index, the incident rate and the reflection rate, their angles that they make coming in and going out, checking our math up on the board right here. So I talked kind of fast today, but I wanted to show you the notes, show you what we're studying right now, not just about light, not just about the eye and the parts, but about how the eye interacts with the brain, getting the information to the brain and how we interpret that as light and how we use that information to make sense of the world around us. Again, check out the Dr. Eagleman special if you have a chance. They have most of it available on YouTube, and it's an excellent little slice of how you can take a lot of what we're doing here with visual things in class and apply it to learning and remembering things more efficiently at school. Okay, take care of yourself.